It is the end of 2017, and this has been a great year for Software Engineering Daily. We're taking a break over the holidays, but we're going to be back after New Year's with a lot of new content. And for now, we are replaying a few of the most popular episodes from the 2.5-year back catalog of Software Engineering Daily. And we've removed the ads to make for a smooth listening experience. If you're taking some time over the holidays to listen to some Software Engineering Daily, take a break from your interaction with the family, go for a walk with a nice old episode of Software Engineering Daily, you won't have to skip over any ads or feel obligated to listen to the ads to support Software Engineering Daily. Consider this a vacation for the both of us. We have big plans for 2018. We've got new types of content coming. We've got more in-person events, meetups, but also more of the same. Long-form interviews about technical software topics. That's what I love to do, and I think that's what most people are listening in for. And as we make our way into the new year, I would love to hear from you and know what you're interested in hearing about for 2018, or who you are, or basically anything. Send me an email, jeff@softwareengineeringdaily.com. Join our Slack channel. You can find a link at softwareengineeringdaily.com if you want to talk to more engineers within the community. And you can also sign up for our newsletter, which you can find on softwareengineeringdaily.com at the top of the page. In the newsletter, we will let you know about upcoming live events and other developments within the world of Software Engineering Daily. As always, thanks for listening and happy holidays. Stephen Wolfram is the founder and CEO of Wolfram Research, a company that makes computational software including Mathematica and Wolfram Alpha. Stephen, welcome to Software Engineering Daily.
Hi.
So I want to start by thanking you because calculus was made a lot easier to learn with Wolfram Alpha, and there were also some days where I would sit down to check my answers and I would get distracted by all the cool things you could do with Wolfram Alpha, so thank you for that.
You make me feel old, you see. For me, the Wolfram Alpha was, the fact you can say that just makes me feel old, but that's good. Thank you.
What inspired you to start Wolfram Research?
Oh, gosh, it's a long story. So, back in the day, so I grew up in England and I was sort of I got interested in science when I was really young, so I was kind of got to the point where I was able to do physics research and things like that when I was in my kind of early to mid-teens and started like writing physics papers and stuff like this. And one of the features of doing physics is that you end up having to do lots of kinds of mathematical calculations and so on, which I always found really boring. And I kind of was in the mode of saying, this is really mechanical stuff. One should be able to get a machine to do this. So that got me interested. This was kind of mid-1970s. Got me interested in, okay, can one actually get a machine to do this stuff? And at that time, there were some experimental systems that people had started to build to do these kinds of things. So I learned how to use them and got really involved in that stuff. And then, went on and became a physics professor and things like that, which I was lucky enough to do by the time I was 20. So I managed to not get completely submerged in the education system for too long. But one of the things that happened was, in order to kind of make progress in doing things like fancy physics things, I needed to be able to do all sorts of mathematical calculations, and I eventually came to realize that the systems that existed for doing these things weren't good enough, and the only choice that I had was kind of build my own. So I started, this was late 1979, I started building my own system for doing mathematical computation, and that became, as my first big system I wrote, it was written in a very newfangled language at the time called C, and it was had all sorts of quite modern software engineering features actually. And it came out. First version was in 1981, I guess, and that at that time I was a professor type at Caltech, and I sort of imagined that was what I would go on doing, but it turned out I realized that my software system kind of needed some commercial home, and so I ended up, a slightly long, complicated story, but I ended up starting my first company around that software system, and that company sort of eventually diverged off into the sort of venture capital morass of, there are shinier things to chase and so on, and I kind of unraveled from it. I went back to doing a bunch of basic research, but then in 1986, I'd kind of managed to I sort of was involved in starting up this kind of area of research that these days mostly gets called complexity theory, and I'd managed to figure out a bunch of things that I thought were pretty interesting from a science point of view, and I had kind of started sort of organizing institutes and things around complexity research, and I realized that in order to kind of make the best possible progress I would need kind of better tools, and so I then realized, well, the best way to get better tools is to build them yourself, and so then that got me into building Mathematica. I also realized that one strategy for getting a lot of science research done is to start institutes and get other people involved in doing it. I realized that was probably not the best path as far as I was concerned, so I decided the best thing for me was to set myself up with the best possible tools and environment for doing the things that I wanted to do, and that involved starting a company and building software system. And so that was how I came to start building Mathematica, and came to start Wolfram Research. And I've been kind of lucky enough to have a sort of simple private company for the last, 28 years or something now, that has kind of let me work on a lot of very long-term, large-scale projects with only my team at the company tell me why I shouldn't do some other new project or whatever. I don't have investors or anything telling me that. So that's allowed me to do things like build Wolfram Alpha, which was a completely crazy project, building a sort of computational knowledge system that's supposed to kind of know about everything in the world and be able to answer questions using natural language and so on, was one of these couldn't possibly work projects.
So couldn't possibly work from the standpoint of your team, or were you unsure yourself if you could actually create a complete computational engine?
Well, so I had been thinking about that since I was a kid, and I had kind of sort of reassessed the thing probably every 5 or 10 years for quite a number of years. And my assumption had always been that to make something kind of like Wolfram Alpha that could be sort of a broad computational knowledge engine, that you would kind of have to make a brain-like thing first. That was my original assumption back in probably early 1980s. Then I ended up doing a bunch of basic science, one of the lessons of which was there really isn't a bright line distinction between what is intelligent and what is merely computational, so to speak. And so that kind of got me to realize, well, gosh, this thing I've been interested in for a long time, maybe it can be done in a sort of merely computational way without having to reproduce a brain, and maybe it can even be done better in a merely computational way. And so I started trying to build it. And there were many questions like natural language understanding. There had been a long history of people doing particularly natural language processing, a little different sometimes from natural language understanding, and it hadn't been a very good history. And the question was, why would we succeed when lots of other people had failed? And turned out, the answer, there were several answers to that. Probably the biggest answer to the natural language understanding question was that we built a very large knowledge base, and being able to do things like disambiguation of natural language is just vastly easier, even feasible, when you have underlying knowledge about the world than it is if you're abstractly trying to say, well, what are the statistical characteristics of this word or something like this. And the other thing was that we figured out a bunch of things that came out of some basic science that I'd done, which let us sort of sidestep a lot of the issues that have been people have been kind of concerned about in computational linguistics and so on.
How would you differentiate the goals of Wolfram Alpha from the goals of Google, like the Google search bar?
The search engine?
Yeah, the search engine.
Well, it's searching the web, right? So whatever people put on the web, it's trying to give you pages that it thinks are relevant to the query you've typed in. What we've been interested in doing, what I've been interested in doing, is kind of taking the knowledge that exists in the world and making it computable, so that given that sort of base knowledge, you can compute the answer to any specific question somebody asks. We're not saying, okay, somebody typed in these keywords, so feed them this page. We're trying to say, given this specific question somebody asked, like, one of your calculus questions or something, although that's a, pretty specialized end of things, can we compute the answer to that question? Can we compute some answer to some medical calculation, or can we compute some answer to something about, I don't know, where will the space station be in, an hour or something like this?
Yeah.
What we've ended up doing is collecting really a very large amount of kind of primary raw data, actually large compared to the text content of the web, and then using that together with lots of algorithms and sort of methods and models and things that come from science and engineering and other places to be able to actually, when you ask a specific question, we try to give you a specific answer to that particular question. And the vast majority of questions that we get asked are ones that, even though we've had, billions and billions of questions asked of us, they're questions that have never been asked before. And they're questions where if you were to type that specific question into a search engine and say, okay, where is that on the web? The answer is it's nowhere on the web. It's not, nobody ever wrote down that specific question before.
Yeah, that makes sense. So let's discuss the Wolfram language. What is the Wolfram language?
So it's sort of the outgrowth of what I've kind of been working on for the last 30 years or so. It's always nice when the things one's been working on kind of come to fruition, so to speak. Kind of the idea of the Wolfram language is to provide sort of as automated, as high-level a language as possible with as much knowledge built in as possible. Sort of the idea is a human wants to get something done by computer. What's the most effective way for the human to describe what they want to have done, and then for the computer to, as automatically as possible, do what they're asking? And kind of the traditional approach of computer languages has been keep the core language, the core sort of designed language fairly small, maybe and have that core language really just deal with very fundamental operations of the computer, together with some structuring of large-scale programs and things like this. But if you want actual content, well, there are libraries, there are, download this, do that, et cetera, et cetera, et cetera. My goal in the Wolfram language has been to sort of build everything into the language. So, there are 5,000 core built-in functions of the language that cover things from, finding, the weather at any time in where there's recorded data, to, solving the traveling salesman problem, to, rendering some fancy, kind of graphics, to dealing with things in the cloud and so on. And it's been, it's sort of a big effort. Go ahead.
So you call Wolfram language a knowledge-based language. How do you define the term knowledge-based language?
It knows stuff. Most languages don't purport to know anything. In other words, in our language, the things I was just mentioning, like, I don't know, it knows what the density of gold is, or it knows what something about the English language, about common words in the English language, or it knows about things about maps of the world, or it knows how to compute distances on the moon or something like this. So the thing is to have these kinds of things built into the language. So there's some function called geodistance or something. We'll just compute distances, and the when you use the language, actually there are a couple of bigger things to say perhaps. I mean, one thing's perhaps interesting is it's been interesting for me at least is the sort of the comparison between Wolfram Language and Wolfram Alpha. So Wolfram Alpha is this knowledge engine thing where you just ask it questions in natural language, and it tries to generate sort of a report that tells you as much as possible about what it thinks you want to know. And this idea of using natural language for that is a great way to do kind of one-off questions. What's the population growth rate in Italy versus Spain or something? An easy one-off question. You can get a nice report. It'll have nice graphs and all kinds of other things. That works well. Now, if you say, well, okay, I want to write a big piece of code. I want to write an app or something. Well, you can start saying, here's how my app should work. You start describing it in natural language, and pretty soon that falls apart. It's pretty hard to describe in a sensible way. You wind up writing something in natural language that sounds like a piece of a patent or something like this. It's very natural language is not a good match for describing more complex kinds of structured things, and that's where having a computer language works really well. If you have a language but the thing that I've tried to do in Wolfram Language is to sort of leverage what people know from natural language. Like, as I mentioned, it has 5,000 built-in functions which have names that are basically derived from words in English, so that you can kind of know what they should be. And when you look at a piece of code, you can pretty easily tell what the piece of code is doing. But the thing which is pretty interesting to me is this kind of interplay between the pure natural language thing for kind of one-off, quick kinds of things, and the structured computer language approach for, make the bigger program. And the really fun thing, which I hadn't really anticipated how powerful it is the interface between those two things. Because, for example, when you're programming in Wolfram Language and you say, I want to know, and you need to put in, in some program, you need to put New York City into the program, or you need to put a list of, 5 cities or something that are, I don't know, the hubs for an airline or something. Well, how do you enter New York City? Well, you just have to enter, in a typical interface, it's, you type control equals. I mean, it's something different on mobile, but you type something like that, and then you can type NYC, and it will then turn that into this, that's natural language, but it will turn that into this canonical thing that is a unique representation in the language of New York City. And you can do more complicated things like that. But this thing that you can sort of enter, particularly real-world kinds of concepts, using little fragments of real-worldism, so to speak, into the language using natural language, I had not anticipated this, and it turns out to be really powerful.
And so one thing that's interesting about it is if you enter something into Wolfram Language, it seems like it's kind of part query, but it's also, you could be setting a variable, and that by setting that variable, you would be making a query like, set X equal to all my Facebook friends or something. So how do you think about those two different things? The fact that you're kind of writing a query language, but it's also like, an actual programming language.
Well, I mean, it's a language which lives both on the desktop and in the cloud. I mean, you can write it both on the desktop and in the cloud, but it always has the ability to go to our knowledge base in the cloud and get extra knowledge. It has a lot of stuff that's built into the actual engine locally, but it also it's always assuming that it can go find more knowledge, find the map of such and such a place or something from the cloud. I think that's at first it was like, oh, this is very, this is exotic. And then it's like, of course, this is how I assume it always works. I think in terms of the structure of the language, well, you mentioned setting variables, and that's kind of amusing. I just finished actually writing a book that I didn't think I would have to write, but I eventually decided I did have to write it. It's called Elementary Introduction to the Wolfram Language, which is basically it's an introduction to the language that assumes people haven't programmed before and things like this. Anyway, it's kind of one thing that I found amusing about this book. It has 50 sections, and I don't mention assigning values to variables until section 37. And that's because it's, the language is primarily a functional language. And what's kind of amusing is that I've talked about how to, deploy web apps and things before I've talked about assigning values to variables. Because it just turns out assigning values to variables isn't all that important in writing at least small programs in Wolfram Language. But I mean, that's an aside, perhaps. But I mean, I think the thing that's interesting, I mean, because we have kind of all this knowledge built into the language, it's very easy to write very small programs that do interesting things. Like kind of the extreme case of this is we have this thing called tweet a program, where you can send, less than 140 character programs into some server of ours, and it'll run them. And people have done all kinds of amazing things in 140 characters. And what I find more amazing is that most, not all, but most of the tweetable programs, if you look at them, you can understand what they do. I mean, it goes from that to probably, I don't know for sure, but I'm guessing that Wolfram Alpha is the biggest Wolfram language code base, and it's about 15 million lines of code now. So it kind of goes from the very small to the quite big, and it's
something interesting that you said there was you were talking about writing this book and how you didn't get to setting variables until section 37, largely because the Wolfram language is a functional programming language. This is actually part of a week of shows about functional languages, and it's interesting because many of these functional languages that we're showcasing, like Lisp and Erlang and Haskell, they're older languages, and it seems like the traits that have made them appealing are only becoming more valuable and more desired over time. This kind of resistance to statefulness and the other beneficial features that you get from a functional language. What are the things that the Wolfram language benefits by thinking of itself as a functional programming language?
Well, so you have to understand it's both a functional language and a symbolic language. And it's Lisp is sort of in some ways a symbolic language. Wolfram language is a much more symbolic language. So the thing to understand first is what it means to be a symbolic language. So usually if you type in X in a typical language and you haven't said what X is, it will say, error, you have to say what X is. In our language, X can just sit there and be X. So, that's nice if you're doing math and you want X to be some symbolic variable. But much more interestingly, X can represent all kinds of different things. Like you can have a symbolic thing that represents New York City, or you have a symbolic thing that represents, some document or some piece of graphics or something like this. Or you can have a symbolic thing that is a piece of code. And the fact that all those things can be kind of represented in the same way as symbolic expressions is pretty critical to the language. And the fact that you can kind of pass around little fragments of code, people who write in Wolfram language they pass around pieces of code all the time. It's kind of like a standard thing you do. And it's just a little lump of symbolic stuff that you can then work with, and that's like really, really powerful. Like if you look at the code base, the Wolfram Alpha code base, for example, it's natural language understanding stuff. For instance, is just absolutely full of things which are kind of a mixture of data and little fragments of code. And the ability to do that, which kind of comes from being sort of a mixture of symbolic and functional and so on, is really useful. The other thing Wolfram language has is it's very strongly based on pattern matching. So, for example, when you define a function, all you're really doing is defining a transformation rule for a pattern for expressions. So, you might say, you could say something like f of x blank equals whatever it equals. And that means f, where blank stands for anything, and then x is the name of the anything, is transformed into such and such. But that left-hand side doesn't just have to be, doesn't need to be just f of x blank. It could be, f of some list, x blank, comma y blank, comma x blank or something. And that defines a pattern. And only whenever the language sees an expression that matches that pattern, it will transform it into whatever the right-hand side was. And that's how the system works, has worked for 27 years. That's the sort of fundamental thing that the system is it's the thing that makes symbolic transformations on expressions. And again, that has what's turned out to be the case is that set of ideas around sort of symbolic programming has so the thing that's happened. So I kind of worked on developing these ideas in the first system that I built back in 1979 to 1981, and in a sense, that system was in some ways more extreme than Wolfram Language in terms of the ways that it used functional and symbolic programming, and in fact, it just said obstinately, you can't do programming. You can't use any of the constructs you might think you would use for programming. You simply have to use kind of transformations of symbolic expressions and so on. When I started building Mathematica, which kind of turned into Wolfram Language, I was a little bit less draconian, but it's still very much based on this idea of symbolic functional programming. The thing that has been sort of super interesting to me over the years is that these different kinds of things, different kinds of programming that I wanted to do, turn out to all fit beautifully into the symbolic paradigm. So, for example, early on, a trivial one is, graphics. Okay, you can represent, graphics and geometry and so on symbolically. Well, that's kind of nice if you're just in terms of writing code to, make things that you can render in nice ways and so on. It gets more interesting when you actually can do computational geometry directly on these symbolic things and say, okay, I've got these symbolic things. What's the volume of this combination of symbolic objects and so on? That's one early thing. Then we realized, documents can be represented this way. It's kind of like, it was XML before XML, so to speak, way back long, long ago, but something where you can actually manipulate the structure of the document easily within the language. Then we realized user interfaces work that way too, that you can have a sort of symbolically represented user interface that you can manipulate at a symbolic level and generate at a symbolic level and so on, and then deploy and such like. And there are just a whole sequence of these things. The one that has been most interesting recently is the realization that one can represent the deployment of programs symbolically. And that's something that, a big thing is kind of thinking about the cloud. And in our language, a cloud object is just another kind of symbolic thing. And you can take, like you can write the sort of the one line, web app just says, cloud deploy. Actually, it kind of shows a bunch of different things that are going on. So a typical...
Wait, what are the properties of a cloud object?
It's a lump of symbolic code that sits in the cloud. And it can represent an API, it can represent a web app, it can represent a bunch of different things. So
very interesting.
So, I mean, to give an example of, this is kind of weird to do in pure voice, but I can try. The minimal kind of web app. So let's say we want to deploy a web app that is going to be a form where you type in the name of an animal and you get a picture of that animal. Okay? So the question is, how would we do that? So first question is, how do you, if you were just doing this in a notebook, which is what we call our interactive documents that people use to program in Wolfram Language, what would it look like in a kind of notebook REPL type environment to say, type in the name of an animal, find an image of it. Okay, so you'd just be able to say something like, let's say you type control equals, because that's the way that you say, I'm going to type piece of natural language, and then you type rhino or something, you hit return, and it would say rhinoceros, and then you type, brackets, quotes, image, and it would be, that would then, it would go to the cloud probably, unless it happened to be cached locally for some reason, and, retrieve a picture of a rhinoceros, and that will be the output. Okay? So now let's say you want to make that into an app. The way that would work is you would make a thing called a form function, and form function has basically two pieces, a thing that says how to set up the form, how to define the fields in the form, and then what to do with the data that comes from those fields. Okay, so the way you'd set up the fields is you'd give a name to the field, like you'd say, I don't know, animal or something. It quotes animal, arrow, and then quotes, and then what you give then is the name of an interpreter type. So in a natural language understanding system, there are, I don't know, 1,000 different domains of kinds of things that one can talk about as kind of entities. And one of them is animals. So you'd say animal there, and that would mean that the field that you get in the form you're going to build is a field that is kind of a smart field that is expecting natural language that represents the name of an animal. Okay? So then the second part of this form function is something which would say, I mean, it's like very trivial in this case. It would be, hash sign, the name of the field, open brackets image, ampersand, and the ampersand is a thing that indicates that that's a pure anonymous function that is going to be applied to a thing we call an association, which is a key value list that contains the data from the fields, in this case just this one field. Okay, so you've got this form function thing. You can type it in a notebook, and it would just sit there as a symbolic thing. It would just say form function. You could actually run the form function. You actually give it data in the notebook if you wanted to. But more interestingly, you would say cloud deploy of that form function, and then what you would get back is a UUID of a cloud object for a cloud object. You click on that, and there will be a form on the web that would have a field that you type in, I don't know, something like whatever natural language you want for a sea lion or something, and it will go off and run that little piece of code and give you the result. So
very cool.
And kind of what happens. So that's what happens if you like to make a web app. If you want to make an API, instead of a form function, you would use an API function, and then in the initial way that's set up, you would get just a web API that is at that URL, and you go there and it'll run that little piece of Wolfram language code and give you the result back. So I mean, what's sort of interesting from a programming language point of view, I mean, that example actually kind of shows a few different things going on. I mean, it shows kind of natural language understanding stuff. It shows kind of functional programming stuff. It shows kind of the fact that the whole thing is just a symbolic object. This form function or API function is just a symbolic object, which can then be, and then its deployment, it's sort of like the API function is a symbolic object that represents a deployable thing, which you then just have to say cloud deploy to actually make live in the cloud, so you can call it from other programs or whatever else.
Right, got it. I'd like to talk a little bit about software architecture. You've mentioned that you've been kind of incubating this language within the various pieces of software that you've created over the last 25 or 30 years. What is the process of pulling things out of these previous projects or breaking them up into, I don't know, services that you access with the Wolfram language? Or I'm just curious how loosely coupled the different components of your older pieces of software are and how you wired them to be accessible through the Wolfram language.
They're all really one thing. So the whole Mathematica software stack is now part of the Wolfram language. The whole Wolfram Alpha stack is part of the Wolfram language. And then somewhat bizarrely, and it's always difficult to explain, the Wolfram language now becomes the thing that powers those other two products. So
it's the superset of everything.
Yeah, it's really one uniform stack. I mean, the real challenge, in all of this is maintaining coherent design of a language that is a huge language at this point that's been, growing for 28 years. And that's been both, I think, that's probably my proudest achievement, if there is one, is maintaining that coherence, because it's hard work. It's what I do every day, so to speak.
What kinds of technical debt do you have?
I don't know. So there are two different levels of that. One level is design, and another level is implementation. So from a design point of view, I was sort of lucky that I had built one system before I started building this one. So I had made a bunch of mistakes in the first system. This in what's now Wolfram Language, there are not a lot of design decisions that I made that I regret. I mean, I'll give you an example of one type of design decision that one regrets, okay? So, you're naming all these built-in functions. And, one thing we're proud of is if you take a Mathematica version 1 piece of code, then with very high probability, it will run unchanged in today's versions of Wolfram Language, 27 years later. So that's, I think that's cool. And we've kind of made sure that that's the case. And it's also important for us internally because a large fraction of our own software stack is written in our own language. But one of the things that happens is, you give a name to something, like you say, assigning values to variables. There's a function, it's called set, that assigns values to variables. Okay, so now many years later, you might say, gosh, I wish I hadn't called it set. Nobody ever types that anyway. They just type an equals sign. And now I can't use set to represent, a mathematical, unordered set type thing. So there are a few things like that. That's one of about 3 or 4 or 5 maybe things of that type where it's kind of like, and gradually over time, sort of I've learnt how to be sure that I know what I'm talking about something to the point where I feel like I can, make a design decision and never have to regret it. And when one has to design defensively, where one's saying, I'm going to give a very complicated name to this function because maybe in 5 years we will figure out a more general way to do this, and then that complicated name can still be there, meaning this very specific thing, but we'll have a more general way to do something more general. That's one kind of thing. When it comes to sort of internal software engineering, I mean, we've we've had a pretty serious program of kind of renewing things over the years. One thing that's nice about there's plenty of, we tend to sort of go through different areas of sort of algorithmic work, and I would say that it's pretty common that we will get to the we'll build our own frontier for some particular area of algorithmic work that goes, beyond the current state of the art. And then, empirically, it seems to last, maybe 15, 20 years before we have to come back in and say, okay, there's now more known about how to do this. We can improve these algorithms and so on. So I think that's, in terms of sort of kind of software infrastructure kinds of things. A lot of our system is written in our own language now, which really helps. In terms of user interface stuff, that has been, we've had a nice uniform desktop user interface that's very well developed over the course of perhaps 20 years now. At the beginning, that was absolutely horrifying because we had, all these different platforms, and then somehow in the mid-90s, they all merged beautifully. Well, now, very horrifyingly, we're back in that state again because we've had to build, a completely custom user interface for using Wolfram Language in the cloud. It's basically a big lump of JavaScript and a bunch of server-side stuff, and that is a complete, it's a completely separate branch of code from the very big user interface that we've already built for desktops and so on. And then, even more horrifyingly, for mobile, we have to have yet another, separate user interface stack for doing sort of the most responsive kinds of things on mobile. I mean, all of these things, we can get away with not doing this, but we don't have the best performance on these platforms, and we want to get the best performance on these platforms. And I have to say, in our experiences with the cloud, I believe that in my, 35 years or so of doing software engineering kinds of things, the current cloud environment is probably the most hostile to development that I have ever seen. I mean, and the most difficult.
In what way?
A lot of different systems. Well, the fact that a lot of things are based on things like JavaScript, which is kind of like a completely crazy, thing to be at the bottom of a big stack of software. The fact that there are many, many different sort of interoperating systems that don't, some of which are very old, some of which don't, we're sort of doing things which are way beyond what they were originally intended to do. The fact that it's kind of, debugging things in the cloud, I finally decided myself that I was fed up with hearing about all the problems of doing this, and so I thought I would actually, maybe 6 months ago or so now, I decided I would actually go in and debug some detailed aspects of why we had some slowdowns in the way our cloud was working. And, I get in there and I realize, the main thing I realized was that using kind of scientific methods and using kind of our language as kind of the thing to go and, create the tests and look at the results and so on, that turned out to be really powerful. And I was able to figure out what turned out to be a completely ridiculous and horrifying sort of underlying, problem. But, that took me all the way through looking at, pieces of the Linux kernel and things like this. And it should not be the case that when I'm debugging, something about why, APIs sometimes run slower than they should, that I'm dragged through pieces of the Linux kernel. That's kind of that's kind of one of the things which, to me is not, that doesn't make the current environment, clean and easy and great to debug with.
Right. Well, okay. So certainly that's, you've listed some aspects of why the cloud is hostile, but you've also said that it's only in recent times that we've gotten the tools that we need to construct the whole Wolfram language. Are the tools that we haven't had until now, like, are you talking about the cloud, or what other tools are you talking about?
Yeah, the cloud is a big part of it. It's, being able to have this really smooth, large knowledge base sitting in the cloud, being able to have, the cloud is great. Don't get me wrong. It's just rather horrifying. It's like, you can build a spectacular railroad, but actually doing it is, has a lot of messy stuff that has to be done. The cloud as an environment is, I had sort of thought it was a purely utilitarian kind of thing. What I realized is that it's a sort of fascinating centralized repository of computation that, and you can have, particularly as you put sort of symbolic representations of computation out in the cloud, you can have, what we routinely now, we have all these cloud objects. They represent little pieces of sort of persistent computation out there, and they can interact with each other. That is a completely routine thing to have happen. Is different cloud objects will interact with each other. We build all kinds of services on top of them, and so on. It's a nice thing. And I think that the fact, for us, our technology, particularly things like Mathematica, have been very widely used in R&D for 25 years. One of the things that's always been something of a frustration to me is that, we'll see in company X, the advanced R&D group will do fantastic things with Mathematica, and then it's like, okay, what happens next? And it's like, well, we need to deploy it somehow, and we ended up, rewriting it in C or something. I had wanted to figure out how do we let people go sort of all the way from the original kind of idea and R&D thing all the way to, a fully deployed, production grade system. The cloud is what's basically made that possible. Now, as it turns out, there are, having modularized things for the cloud, there are also ways that you can take the exact same, like a piece of code, like one of the cases we're interested in is embedded processors for IoT type things. And you can take the same piece of code, Wolfram Language code, and you can run it with an embedded Wolfram engine on a tiny device. Like, for example, the Wolfram Language is bundled on the Raspberry Pi Linux computer. And you can, take that piece of code that you were running in the cloud, and you can run it on this embedded device. It's even nicer because you can have the cloud communicate with the embedded device, and it sort of all sort of plays consistently together. So that's all of those things. The whole deployability of our language is pretty serious. Having realized how to do it on the cloud, I now realize that we could probably have done it in some ways on other kinds of systems, but it works a lot better on the cloud and through the web and things like this. It's a much easier kind of path to say, okay, like that form function thing I was explaining, you do that, and then instantly, everybody in the world can go to that particular URL and go do this thing, and it's sort of instantly deployed. And that's, I think that's important to. I think that's very important in practice to people, using our language and so on.
Yeah. So I want to shift gears and talk about a book that you've written called A New Kind of Science. What is A New Kind of Science about?
So, well, that's also many years of my life. Here's the sort of where that came from. So, when you look at exact science, for about 300 years, people had kind of been saying, okay, you want to make a model of the universe or something, use mathematical equations, write down some differential equations, that's the way that you make a model of things in the world. I got interested in kind of generalizing that idea and saying, okay, maybe if the thing doesn't fit with mathematical equations, but you still think there's a definite rule, a definite theory for how things work, what's the more general sort of infrastructure that you can use to specify that? And I started looking at simple programs as a way to represent things in the world. And that got me into the question of, okay, if you look at this sort of computational universe of possible simple programs, what do such programs do? And by simple programs, I mean, well, one type of them that I looked at a lot, things called cellular automata, a little bit similar to Turing machines. But in a cellular automaton, like you have a row of black and white cells, and at every step you say, okay, a cell will turn black if its left neighbor is white and its middle thing is black or white, and some simple operation based on the colors of neighboring cells. And you might say, okay, if we have a program that simple, all it could ever do is show very simple behavior. But the thing I discovered in the mid-'80s is that simply isn't true. I did the obvious computer experiments and found, to my considerable surprise, and it took me a few years to actually believe it, that even when the rules for the program are incredibly simple, the behavior the program generates can be, in a sense, arbitrarily complicated. And so that got me into thinking about, okay, so what does this mean for modeling the natural world, for how nature works? Nature is remarkably good at making kind of very complex things. How does it do it? And what I kind of realized is the way it does it is the same way these simple programs do it, just some fraction. It's just a fundamental fact about things that some fraction of simple programs generate very complex behavior, and that's how nature is doing it. And that got me into...
Yeah, so a quote from you that I think kind of illustrates what you're talking about is, quote, "The universe is digital in its nature and runs on fundamental laws which can be described as simple programs." What I think is interesting about this quote is I feel like many people have a sense that the universe maybe is more analog, or at least their intuition is that the universe is analog. But I mean, I can definitely appreciate this digital notion, but I could also see that maybe it's drawn some controversy. Have you had any disagreements with people about this discussion?
Well, we don't know how the universe works yet, so it's people can disagree until one knows for sure. I mean, I'm in this funny position because I was a rather successful physicist in the sort of traditional physics community way back when, and then as a result of kind of thinking about things in a somewhat different way, ended up thinking about physics in a really different way, in a way that sort of diverges a lot from a lot of the developments in string theory and all these other kinds of areas. Am I ultimately right in my guesses about how the universe works? I won't know until we've kind of nailed it for sure. Does it seem promising? Yes, it seems incredibly promising. I mean, in the sense that there's, a good test of theories in science is how much do you get out for what you put in. So if you have a really, really tiny theory, that is very, very simple theory, and you can start to explain lots of things, that's a good sign. If you have a really complicated theory and you're having a really hard time explaining much at all, that's a bad sign. By that measure, the things that we can already see from just looking at very simple programs and what they can do and how what they do corresponds to the things you see in relativity and quantum mechanics and so on, it's remarkably promising. Now, do we know for sure? No, we don't. When I haven't been doing technology development, my hobby is kind of hunting for the universe. And what that means is basically, if the universe corresponds to a sufficiently simple program, it's not crazy to go and just start enumerating programs and seeing what they do. And I kind of assumed before we got anything that had anything universe-like, had anything like finite dimensional space and, gravitation the way it usually works in physics and so on, that you'd have to go through, billions, trillions, quadrillions of candidate universes. A thing I found, I don't know, a decade ago or so now, is that even at about universe number 1,000, in sort of an enumeration of possible universes, you're already seeing really complicated behavior. And, you run it in a computer and you try and simulate it and you let it run. It's a kind of a network it builds. And so, you build it out to, 10 billion nodes or something, and it's flapping around and doing all kinds of things. And you say, did I actually find the universe, our particular physical universe in my computer? And it's really hard to tell. And essentially you have to do a whole lot of, you have to sort of recapitulate the history of physics, looking at this thing that's flapping around in your computer and trying to figure out whether the effective physics that it's showing corresponds to the physics that we actually observe in the real universe. And we don't know yet, but I think it is far from impossible that we've already seen a sort of a simple universe that actually is our physical universe. We don't just don't know it yet.
Okay, well, so speaking of things that we can theorize about but not be totally sure about, do you think that we're living in a simulation?
That's a poorly formed question.
Oh, okay. Apologies.
I think that so people say things like, you think the universe is like a program, right? Say, okay, what computer is that program running on? Okay, that's not really a meaningful question, because to say the universe is like a computer is to say, or to say the universe runs according to simple rules, the rules of some simple program, is to say that that's just what the universe does. There's no substrate on which it's running that implements that. It's simply those are the rules by which it runs, so to speak. So now you have to ask the question. This is okay. So now we're going into real-time philosophy, and that's always pretty hard. But you have to start asking questions about. So what would it mean to say that it's a simulation? So the universe, it's doing something, right? There's some. What you would be saying if you say it's a simulation, is you're saying you're distinguishing, in a sense, the substrate from our experience, so to speak. And
yes.
And so, but if you say, if you look at the universe and you look at kind of what, it's very hard to draw that line between substrate and our experience. That is, what counts as something, you might say, well, gosh, there are these absolutely microscopic organisms that exist at 100 times the Planck length, and they're doing some complicated knitting thing, and their complicated knitting is making our universe. So our universe is a simulation implemented by creatures whose size is very, very tiny creatures. Okay, now let's take that apart a bit. To say that in a reasonable way, you would say, well, but I don't believe there are little tiny creatures that are sort of little tiny fragments of the universe that are intelligent, that could do those kinds of things. Okay, so now we have to unravel a little bit. What would that mean? I mean, how would you tell whether this little clump of, let's say it was little nodes in one of my sort of discrete universe models, this little clump of nodes, and it's doing really complicated things, and you say, well, is that clump of nodes doing something intelligent? Is that like a little organism? Or is that just like a clump of nodes that's just working according to definite rules and, it's not doing anything sophisticated? Well, this is what I was kind of mentioning earlier about this kind of, is there a bright line distinction between what is sort of intelligent and what is kind of merely computational? So this comes up, when we start looking at, simulations of brains versus actual brains and so on. Do we say there's something magically different about the actual brain than about our detailed simulation? Or more to the point, thing I've studied a whole lot is, okay, so in the basic science end of this, there's this thing I call the principle of computational equivalence, which basically says if you look at some system and has some definite rules, what you will find is that above some threshold in the complexity of those rules, a very low threshold actually, the behavior that you can get from the operation of those rules is equivalent to the behavior, is computationally equivalent to the behavior you can get from any other system. So what does that mean? So we know that there are universal computers, for example. That is, that you can have a machine that can be programmed to emulate any other machine. What is not obvious is that that phenomenon can happen even with incredibly simple machines. When you say, okay, I'm going to have a computer and it's going to be programmable and all that, you start thinking about CPUs and ALUs and billions of gates and all this kind of thing. It turns out that none of that is necessary. Even incredibly, if you just look at possible simple programs, then within 100, 1,000 simple programs that you might randomly look at, you will run across ones which are capable of universal computation. You'll run across ones whose behavior will typically be sort of as complicated as anything else. And so those programs, they will be as complicated as anything else, including as complicated as brains. And that's actually why, to brains, those programs appear to be doing complicated things. If brains were incredibly much more sophisticated in the computations they could do than those programs, then those programs would look simple relative to what we can do with our brains. But because there's this equivalence, that doesn't happen. So, this question of what counts as sort of intelligence, the creatures who are pulling the puppet strings, so to speak, for our simulation, versus merely a piece of universe that is computationally sophisticated. That's not a distinction you can make. And this becomes very explicit when you start talking about, search for extraterrestrial intelligence. And you say, in fact, this just happened recently, some recent phenomenon where people were saying, it's so complicated it must be, or it's kind of so bizarre that it must be the effect of intelligence. Or not must be, might be the effect of intelligence. And that's and so...
You're talking about the SETI transmission?
Yes. The question is whether, when you observe something complicated in the universe, is it the result of intelligence or is it merely a physical process? Back 100 years ago, people were, first, putting up radio masts and things like this, and they heard all kinds of weird and complicated things in sort of the radio universe. And, I think Tesla was one of the people who was convinced it was the Martians signaling us. Turns out it's, modes in the magnetosphere. It's a physical process. Right. But it's there isn't really, this is it's an important theoretical point that there isn't really a distinction between kind of the intelligent, so to speak, and the merely computational. It's hard to do this. This real-time philosophy is particularly when it's
responding to a poorly formed question.
What's that? No, perhaps did I succeed in explaining why that question is kind of poorly formed?
No, I think it was a great. I love your response. One thing that I find interesting about your work is it seems like you have pursued solving a problem that you yourself had. You like Mathematica to Wolfram Alpha to the Wolfram Language. Each of these problems were things that you really wanted to solve deeply, and I think this is this is something that engineers should generally pursue, is to look for problems that they need to solve themselves. Do you have any advice for people who maybe are like looking for the right problem to work on, looking for something that they can dive into and really get passionate about and start building a lifelong career towards?
Yeah, I think that working on things that you really care about, building stuff that you're going to use yourself, it's fairly critical, both in terms of your own fulfillment and in terms of building things that are actually good and that other people are going to want to use. I have a very, I've worked with a lot of people over the years, and I've been, one of the things I've liked most about building my company is I've managed to kind of, I would say, collect a lot of very talented people from around the world, so to speak. And I've been sort of collecting them for years now. And I find it really interesting to understand sort of how people's careers develop and so on. And I think, I have an ultimately optimistic view, which is, for every person, there's a niche in the world. And, sometimes one is lucky enough to have been born at a time when one is a fit for a particularly interesting niche that exists. Like, I'm kind of lucky that I've been around at a time when sort of computers have just become, I was born in 1959 when computers were incredibly primitive, and I've sort of was around at the time when computers made the transition to not being so primitive and to the point where you could, build sophisticated software systems and so on. And so, I've been sort of lucky in the alignment of, and I've found, for myself, I've been always interested in, what is it that I'm actually good at doing, and how do I map what I'm good at doing into things that make sense to do in the world. And I think that it's usually it's a big puzzle to do that. And I've watched and helped lots and lots of people do that. And the thing that tends to happen, so there are many principles about this. One is if you identify sort of what's new and emerging in the world and, choose that as your career, you'll obviously do better than if you identify something which may have a lot of institutional structure and kind of a lot of people saying, oh yeah, you could do this and be a such and such kind of programmer or something, and there's a million others like you, and kind of one knows how that track works. If you can get into something early, you're vastly better off. In today's world, if you're it's an interesting principle. If you take, if X is any field and you prepend the word computational to it, and then you say, does that computational thing, does it exist? And the best ones to get into are probably the ones that don't really exist yet, because they will all exist at some point. And, I think that, but the thing I've noticed is that it's a big puzzle figuring out what, how you match the things you really like to do with the things that exist to do in the world. And what tends to confuse people a lot is, they go through school and they're good at they might be good at, bad at, like, hate subjects that are taught in school. But those subjects are a very, the sort of the main subjects of that people learn in school they change very slowly. And they are a poor model for what actually exists to do in the world. So, you can hate math, and it turns out that, and you might think that a whole, raft of professions would be, oh no, I shouldn't do that. It's too much like, math in school. But it turns out that it's not, because, the essence of those professions has nothing to do with the essence of the thing that made you not like, math in school or something. So it's always I think the main thing is to realize that it is something of a puzzle. There's something to figure out. It's rarely, if you want to find sort of a unique niche, and those are, if you can find a niche which is sort of uniquely suited to your particular, interests and abilities, that's, well, I don't know. I think that's for me at least, that's always very satisfying to do things where I feel like if I'm doing it, I'm doing it and I'm a reasonable fit for doing it, and it's different from what other people are going to do. At least in sort of my version of egotism or something, that's really good to be able to do things where I feel like if I do it, I'm doing sort of something unique in the world, and it's not just something where, oh, there's 65 competitors who are trying to do the same thing. My typical tendency when it looks like that's the situation I'm getting into is to say, okay, we'll just let the other people do it. I'm more interested in doing the things which are kind of where I can make some unique contribution.
I'm sure you've seen some of the sounding of the alarm about artificial intelligence among people like Elon Musk and Bill Gates and Nick Bostrom. So I'm curious if you think that this is a legitimate concern that we need to be thinking about, and if so, what kinds of measures we need to take to sort of cordon off the potential for artificial intelligence to develop into something that could threaten humanity.
Yeah, obviously, I know about this and thought about this for quite a long time, actually. But well, okay. Again, it's a little bit. I think there's a little bit of sort of philosophical complexity about this. I mean, what is technology? Technology tends to be about automating things. First there are things that humans do for themselves. Then we figure out some way to get technology to do it automatically. Now, as we go on, more and more things which we were thinking were kind of human activities will get automated. I mean, in the next probably 10 years, a lot of kind of professional things will get automated. It's also the case that what will happen, I mean, so one very glib thing to say is yes, the machines will take over, but mostly just because the humans are kind of lazy. And to be more specific, if there was a time when you used to actually have to, look at maps and figure things out when you were driving. Now you just, at least I just set up my GPS and I just follow and do whatever it tells me to do. So similarly, there are many other things where basically machines will tell us what they think we should do. I mean, we've done lots of experiments. I've done a lot of stuff with personal analytics and figuring out, from sort of my history, things about what I might be interested in, what I should do, those kinds of things. Machines will be a lot better at telling us, what is likely to be the thing that we should do, so to speak. And I think a lot of the time people will just, look at the auto-suggest menu and just pick off the thing on the top and do that. And so in that sense, the machines will be kind of in charge. Now, even that scenario shows you a little bit what the issue is. We build technology, we get, an AI that does all kinds of very, very elaborate things. I've spent a large part of my life building AI-like stuff that does elaborate things. The question is, in a sense, there are things where we can say we take something that humans do and we make it automatic. The one thing that, in a sense, there isn't a way to make automatic is defining the goal for what we want to do. That is, there is given a particular goal, there may be some optimal path, there may be some best piece of code we could have, there may be some, best algorithm, whatever else it is, but there is no best algorithm for the goal. There's no way to define what there's no sort of abstract definition of a goal. I mean, we say we're going to build the most powerful possible AI, and, we kind of know what that means in terms of some of the things it will do, but we don't know what that means in terms of what its goals should be. We can sit our AI box on our desk and we can have it respond to all kinds of things we want, but defining its goal is still something that's it's not something that comes with sort of solving the problem of AI. And if we look at, human history, human goals are defined. In fact, it's sort of not unrelated to the question you were just asking about kind of, career tracks and what to build and things like this. What do you pick as the goal? Well, there's no right answer to that. It's something which is a consequence of kind of culture, history, lots of details of how we got to where we are now. So I think that in some sense, the goal structure is something that is it gets meaning only from the kind of the details of the history of human civilization and individuals and all those kinds of things. It's not something where there is an abstract way to solve that problem. Now, in terms of and so, in a sense, that's the. Now, you say, well, how will human goals evolve? Interesting question. I mean, you might say, gosh, if the machines are doing all the work, humans will just be hanging out playing video games. Here's the thing that that one realizes when one starts to think about that. Think about the Middle Ages, for example, and think about what people were doing in the Middle Ages. And, they were, growing their own food. They were fighting off this and that. They were doing, all kinds of things. And, look at the activities that we do today, and a vast fraction of them would be seen by people kind of in the, if you looked at it from the view of the Middle Ages and you said, well, in the future, people will be walking on treadmills. Why would you do that? What a ridiculous thing. That's just like playing a video game. Why don't you just actually walk somewhere or something? So, and I think actually one of the ones I just heard actually from one of my kids was that now there's a video game that consists of people basically writing in assembly language, which I just thought was, nobody writes in assembly language for real, but now there's a video game that does that. But I think, so I think this question about how kind of human motivations will evolve that's probably that's an interesting question. And, I think the most important aspect of that probably is, when there is effective human immortality, which there will be from biology or from technology, that will throw a wrench into a lot of the traditional sort of sources of human motivation, and it's somewhat unclear to me what will happen at that point. But I think that is much more of a human problem than it is it's a problem of it's not a problem of, oh gosh, we'll just be stupid and make autonomous weapons which will shoot at us and so on. Maybe there will be some terrible incidents and so on of that type, but my feeling is that the bigger question is, what's sort of the future of humanity in terms of what people or the end point of the sort of the civilization, what it chooses to do. One of the things that is perhaps a bit I don't know. I mentioned this whole issue about sort of computation versus intelligence and so on, and we talked about SETI and sort of how do you tell the difference between just the modes of the magnetosphere and some very some civilization on the planet Mars or whatever. And one of the things which is a little bit kind of what gives one a little bit of pause is to realize that what perhaps we might see as the ultimate goal of our amazingly developed civilization or something is this very human consciousness all sort of packaged up in some very I don't know, my version of it is my kind of quick way of saying it is the box of a trillion souls, where you've kind of packaged up human consciousness and you've just you put a trillion of them in some little box that is able to let people or the kind of the representations of people sort of do whatever they want and so on. And the question then is, when you have this box and you have all these little configurations of electrons and so on whizzing around that represent all of these effectively engrams of humans or something, you look at this box and you're looking at the thing and you compare it with a rock or something. And the rock also has lots of electrons that are whizzing around doing all kinds of things. And you say, well, what's the big difference between the rock and the box of a trillion souls, so to speak? And I think the answer, the only answer in the end is the box of a trillion souls has that whole history that is, our particular special history with all of the particular details and so on. And, the rock has a different history. And, we should, that's the thing we've kind of achieved in the civilization, is this whole long sort of history of development. And there isn't really a kind of an abstract endpoint where, in the future, technology will get to this amazing, endpoint that where everything will be solved type thing. It's the same thing that there's no sort of ultimate definition of the goal. There's no such sort of defined endpoint. So what ends up being important is the details and so on. I think so. So from that, I think those are some of the issues. I mean, what we will see in increasingly, and it's what I've been trying to build from a technology point of view, is humans define the goals. Our technology, as automatically as possible, tries to achieve those goals. So, when we're writing, Wolfram language code, what I'm trying to achieve is that Wolfram language is the best way to tell the machine what you want to do. As I was mentioning, you can use natural language to tell it small and simple things. When you're telling it more sophisticated things, you end up needing a kind of a rich, structured language, and that's what I've been trying to build. Actually, my current kind of thing I've been thinking about, okay, maybe we can end with this kind of, since you've gotten me talking about all kinds of strange philosophical things, I will end with this thing, and maybe one of your listeners will figure this out, and then they should tell me what they figure out. So it has to do with kind of the history of communication, and you're thinking about different organisms, let's say, different entities, and they're trying to communicate ideas to each other. And sort of the 0th level is what happens genetically. That is that one organism kind of is wired up in some particular way that's a result of its genetics, and as a result, it knows how to do thing ABC. Okay, that's sort of 0th level. The next level is the organism has a brain. The brain is just sort of a generic, mess of neural network. And when the organism, is born, the brain starts to receive data. And for example, when we look at, image identification, object recognition, these kinds of things, this is what happens there, that the brain is kind of a blank slate. And, in fact, we built a nice image identification system that's in Wolfram language. And that was, I tried to do it in 1980, but we didn't have what we needed to do it at that time. So now it finally works. But that's a case where you kind of start from this blank, messy, neural networky type thing. Could be in a computer, could be in a brain, and you just learn from experiencing the world. You learn how to do object recognition, and that's most of the animal kingdom works that way. Then us humans figured out one extra thing, which is we figured out human natural language, and the amazing thing about human natural language is it allows one, across generations, so to speak, to communicate, non-trivial knowledge, so to speak, and that's the thing that I don't think would have been obvious to the people, when there was first human natural language, is that would lead to a lot of what we have in civilization and so on, that this idea of being able to communicate knowledge in a way that is disembodied from the particulars of a brain, that is something where you can go, brain-to-brain transfer of this knowledge. But there's still a serious bug with natural language, which is, I might tell you something, and I'm creating this language to and saying something in human natural language, and then you hear it, and then somehow you have to absorb that knowledge and knit it into what you already know in your brain. Well, what I realized is in today's world we actually have one more level, and what we're trying to do in, for example, Wolfram language is it's a way of communicating things about the world, both the real world and things about sort of how you do things in the world, how you, algorithms and things like this. It's a way of communicating that stuff, and it's in many dimensions at least as rich, if not richer, than human natural language. But it has one important other feature, which is that when the receiver does not have to go through a sort of an independent process of absorption, so to speak. You take that piece of code and it will just run. You don't have to have the receiving entity, reinterpret it. It just immediately runs. And so what I've kind of realized is what happens, and there are many things that this, many interesting things so for example, one thing that many questions that I don't know the answer to. Like one of the questions is, what if a large fraction of people in the world, for example, knew our language and knew how to represent things in a structured computer language kind of way? What would that? We know that literacy 500 years ago or 200 years ago, or whenever you count literacy as having really taken off in the world, led to all kinds of different systems being possible. What does it mean if one has, knowledge-based computer language that is actually known by a lot of people? What does it mean more generally The thing that's really bugging me right now is I'm thinking, when one knew that natural language was invented by humans, could one have predicted a lot of what's happened in the sort of development of civilization and so on? And now that we have sort of another level of ability to communicate ideas, what does that mean for what does that actually imply about the future? And I'm pretty sure it implies some really interesting things, but I haven't quite figured out what they are. And that's my one of my current challenge problems, so to speak.
That's great. That gives me a ton to think about. Stephen Wolfram, I want to thank you so much for taking all this time and being so generous, and for inventing something that helped me learn calculus again. Thanks, and it's been great having you on Software Engineering Daily.
Thanks.